In this video, we're going to be talking about how to write equilibrium constant expressions for a given equilibrium reaction. So we're going to be talking about two different types of equilibriums. We can have an homogeneous equilibrium where you are dealing with all the reactants and the products to be having the same phase, or they all going to be either solids or liquids or gases. But then you can have a heterogeneous equilibrium where their phases would be different, and we'll talk about that in a minute. So suppose I write a generic reaction where I have N2 gas reacting with H2 gas, and it's going to be at equilibrium with NH3 gas. And if I balance this reaction, I would have to have 3 here and I would have to have 2 here. Now, once your equilibrium has been reached, and the rate of forward reaction is going to be equal to the rate of reverse reaction like we talked about in the previous session. Now, how would you know that if your products are going to be higher in concentration or your product going to be lower in concentration, or they may be equal to one another in terms of concentration? And that's something can be explained by writing so-called an equilibrium constant expressions. So the symbol for an equilibrium constant expression is going to be KEQ, and sometimes you also write that as in a KC. So KC just means in terms of the concentration, and you're always going to be writing the concentration of your products to the power of coefficients. So let me just kind of go and write that down, x there. So x means whatever coefficients you have in front of the products in a balanced equation, divided by the concentration of your reactants to the power, let's say y, and y is, in this particular case, is going to be the coefficient you have in front of the reactants. So like in this particular case, I would go ahead and write down the concentration of NH3, because that's the only product I have, to the power 2, because that's what we have in front of this NH3 as a coefficient, divided by the concentration of N2. So N2 has only 1 as a coefficient, so you don't really have to write 1 as in a power. It just automatically means there is 1 in the power if you don't write anything. And then times the concentration of H2 to the power 3 in this particular case. So that's going to be a typical way of writing the equilibrium constant expressions for every single reaction when we're dealing with the same phase. And I can go ahead and talk about maybe another example. So suppose I have this organic reaction where the CH3COOH liquid is going to be reacting with CH3OH liquid, and then it's going to set up an equilibrium with the products that would look like CH3COO CH3 plus an H2O. So everything is a liquid in this particular case. There is a common wrong understanding among the students that if you have liquids and solids, you don't really include in the equilibrium constant expressions. Well, that's not necessarily true. There are times when you can still going to be including your liquids in the equilibrium constant expression. Like for this particular reaction here, your Kc is actually going to be the concentration of CH3COO CH3, and then that's going to be liquid, that's going to have a power of 1, and then I got water to power 1. Divide that by the CH3COOH, and then times CH3OH. Now, under what conditions you don't really include your liquids and solids in your constant expressions? When first you're dealing with a heterogeneous equilibrium, and the second requirement is those particular liquids or solids are going to be so much or so huge in amount that they will not affect the equilibrium concentration in that particular case. So those are the only times when you don't really include solids and liquids. You may see in the books writing all the time, okay, you never include solids and liquids. Well, that's mostly true, but the true statement is whenever their concentration is so high that it does not affect the rate or it does not affect the equilibrium constant value, that's when you don't include those. So let me take an example here. Say I have HF aqueous plus H2O liquid, and it's going to be in equilibrium with the H3O plus and F minus, and all of those products are also going to be in aqueous. So when I'm writing the equilibrium constant here, and I can just write down KEQ for right now, but this particular one is also going to be KA. That's something you will later learn later on, but just let me write down KEQ for right now. So I'm going to be including the concentration of H3O plus times the concentration of F minus. Divide that by the concentration of HF only. I'm not including the concentration of H2O, and the reason I'm not really including a concentration of H2O because it's first a liquid in phase, so it's different than what other reactant and product species I have, and then second, the H2O is actually going to be used as a solvent. So you're just dissolving this HF in water. So this water, since it's so much in amount, it's not going to make any difference in the equilibrium constant value. So that's why you're not going to be writing that particular one in the equilibrium constant expression. So let me take another example. So suppose I have CaCO3 solid and it gets broken down into CaO, calcium oxide solid, plus CO2 gas. So now again, I'm running into a heterogeneous equilibrium where I got some solids and I got some gas here. So when I'm writing the Kc expression, it's only going to be the concentration of CO2. That's pretty much it. And the reason why we don't really include the other guys, first, they are hetero, so they got the solids in there, and the second, their concentration is going to be so high that it will not make any difference in the values of Kc. Or another way of saying, whenever you're dealing with those separate liquids and solids, you take their concentrations to be 1, or you take their values to be 1 so that they don't really affect the concentration, equilibrium concentration values. So let's try another one here. So how would you write maybe suppose I got phosphorus plus O2 and it goes on to make P2O5 and your phosphorus is going to be solid, your O2 is going to be a gas, and this P2O5 you actually make is going to be a solid as well. Well, make sure you balance the equation, and to balance this equation I would have to put 5 here, 2 here, so that's 10 oxygens on both sides, and you're going to have to put 4 here for the phosphorus. So when I'm writing the Kc expression, or the equilibrium constant expression here, so remember I have the solids here, the P2O5 and the P here. We're not going to be including those. We're only going to be including the gases and the aqueous. And in this particular case, the only gas I have is the O2. So that's going to be 1 over the concentration of O2. Why would I put that in the denominator? That's because your O2 is the reactant, and that's going to have a power of 5 in there. So a general analogy or general trend you're going to be seeing in Gen Chem, you always going to be including the reaction, including the reactant and the product species that has either the gases or the aqueous. And as far as the other ones go, like if you're dealing with a heterogeneous equilibrium, and in that heterogeneous equilibrium you have solids or liquid along with the gas and the aqueous, you never include the solids and the liquids in that particular case. But like I said, if you're dealing with a homogeneous mixture, where homogeneous equilibrium where we have everything is in liquid, like we talked about this particular example here, then you don't really have anything but just those liquids. So in that case, you do want to include everything in there. So that just applies to the heterogeneous equilibriums. And another take-home message here is going to be if your Kc is greater than 1, then you can say your reaction is going to be, or your equilibrium is going to be product favored. And if your Kc is less than 1, then it's going to be reactant favored. And, occasionally you may get Kc exactly to be equal to 1 or approximate equal to be 1. In that case, you're going to have the concentration of your reactants to be equal to the concentration of product. So that's unlikely to happen. I mean, doesn't necessarily mean it will not happen any time, but it's unlikely. It's very low odds happening that way. But make sure you know, like if your Kc is bigger than 1, then you would have more products than the reactant, so it's product favored. And if your Kc is less than 1, then you would have more reactants than the products. In that case, it's going to be reactant favored. So that's another type of question you may see in the exams. So hopefully this was helpful. If you have any questions, feel free to leave any comments in the section below. And on the third carbon, it's going to be going down